Great, so thank you all for coming to this month's seminar. Pleased to welcome Sarah, Sally, and Roger from TERC and Tufts University. They have already put some time, so I will let them take it over from there, say a few words, and start the presentation. Thank you.
Thank you. We're going to talk about a project that we've been working on called Focus on Energy. It was funded by the National Science Foundation, and Sally and I are from TERC, Roger's from Tufts, but we were also worked with colleagues on the West Coast at Seattle Pacific University and Facets Innovation, and also with Boston College with a psychometrician. So we're going to, our challenge was to introduce energy teaching and learning in the 4th grade, and we're going to talk to you about the project. To start it off, I'm going to show a video. This is a video that we made for the NSF Video Showcase. It's only 3 minutes long, and I think it does a nice job of introducing the project.
When you look at these images, can you tell a story about energy? Where is the energy coming from? How is it changing? How do you know? Now imagine 4th graders looking for evidence of energy in these same scenarios. What do they have to say? They have many ideas about energy, but are missing a framework to tie them together. Current science and engineering standards call for students to begin learning about energy in elementary school. Unfortunately, many elementary teachers feel unprepared to teach about energy. They need both a solid understanding of the science and tested classroom activities and materials. The Focus on Energy project provides teachers with professional learning and classroom activities so they're ready to teach about energy in grades 3 through 5. We use an innovative approach. We introduce students to a framework called the Energy Tracking Lens that helps them reason about energy across the science curricula and in everyday life. Students investigate phenomena involving motion, electricity, and heat. Whether it's a collision, a wind farm, or photosynthesis, there's an energy story. With the Energy Tracking Lens, they use representations to make the invisible visible and to reason about the energy flow. They begin to look at energy through the eyes of a scientist and to ask a set of key questions.
Actually, 2 lectures. Yeah, it's all electric. No, this is all also motion.
Is there a transfer or a transformation?
Focus on Energy provides a coherent system of resources and supports: a summer workshop, classroom tested activities, formative assessments, and school year professional learning. Both teachers and students are finding the Focus on Energy activities engaging and motivating, and we are seeing students learn to use the energy tracking lens remarkably quickly. Energy is abstract, but the Focus on Energy project is bringing a new level of reasoning about energy to elementary classrooms.
I didn't want to do that. There we go. So I'm Roger Tobin. I'm in the physics department at Tufts University. So I'm a physicist by training. My background's in experimental condensed matter physics. And I've come to this field of working in education in the schools fairly late. And we'd worked together on some other projects. And when Sarah came to me with this idea of this project, I was kind of skeptical, to be honest, because energy, I should say, first of all, that when we say we're teaching about energy, we're trying to teach about it from a scientific perspective. Scientific perspectives on energy as a quantity that's not in the sense of a resource or a social problem, but in the sense of how we think of it as scientists. So I had to think about, how do we actually use energy as scientists, and how can we make that meaningful to children who don't know algebra, don't know fractions yet, because energy is fundamentally a quantitative idea. It's all about counting, really, and we needed to find ways to make this accessible. So that's one of the challenges, that it's a quantitative idea, and yet we're working with students and teachers, for that matter, who don't have a lot of quantitative skills. In addition, it's a fundamentally abstract idea. You can't see energy. You can't measure energy. You can measure things that are related to it, but it's not something you can hold in your hand. So whenever you talk about energy, what you're really doing is you're modeling. It's a scientific model. It's something that we invented to explain how things behave. And in fact, if you go around and talk to physicists, you'll get disagreement about whether energy is actually a real thing in the world or not. Some physicists, I happen to be one, believe it's a thing, that it actually exists. But others say, no, it's just a mathematical construct that we use to analyze things that exist. It doesn't matter. It doesn't prevent us from doing things. But it's just one indication of how fundamentally obscure this idea is. So there's a lot of challenges associated with this. And we've spent a lot of time trying to figure this out. And so these are challenges not only for the students, they're challenges for the teachers. Another thing that we know from the research is that the educational system that we have for teaching about energy is stunningly ineffective. Studies of how much students know about energy in elementary school, in middle school, high school, college, shows that there's very little progress. The naive ideas that people bring in as 10-year-olds have not changed very much when they're 30-year-olds, even if they've had normal education. And that, of course, is what our teachers have had. So not surprisingly, they don't come in with very sophisticated ideas about energy or understandings of energy either, and they're scared of it. And in fact, many elementary school teachers are scared of science, and that comes through when they're teaching science. And I've observed this. This is one of the things that motivated me to get involved in these sorts of projects, is I went to my son's classrooms to help with science lessons, and it was obvious to me that the teachers were terrified. And I thought, if it's obvious to me, it must be terribly obvious to the students, that these teachers whom they love and admire are terrified of science. And what kind of a message does that send? So part of this has to be supporting the teachers. So we'll talk more about that later. But so to do this, we have what we do in the classroom, which involves activities that allow them to explore ideas about energy, representational tools, assessments, and a structure, an intellectual structure that they can work within that we'll be talking about in a minute. Another big part of it is the teacher professional development, and Sally's going to tell you a lot about that later. There's also a whole set of web-based resources that we've developed, which we're not really going to talk about today, but we can give you a link to that if you want to look at some of the stuff. So it's a system. It's a whole system of resources. So there's been a lot of research about thinking about energy and teaching energy, and the consensus is there's sort of four big ideas that you have to get to think reasonably about energy. So the first is, and there's controversy about this, but there's an idea of forms of energy. Okay, you can have energy that's associated with motion, energy that's associated with thermal activities, energy that's associated with things that are being stretched or distorted in some way. There's electrical energy. So there's this idea that energy manifests itself in different ways in the real world. And associated with that is the idea that energy is something that can move around. It can move around between objects and systems, and it can also move around between these manifestations. So energy that's now manifested as the coiling of a spring will later be manifested as motion or heat or something. So there's this idea of transfer and transformation. Then if you're actually going to get to what we really want to get to, which is the idea of energy as a conserved quantity, eventually, you need to understand the idea of dissipation, that one of the kinds of transfer and transformation that can happen is that when things seem to have come to a stop, that energy is not just gone, vanished. One of our students said, gone to energy heaven. It's actually somewhere in some form. That's actually an extremely difficult concept. And then there's fundamentally the goal, which is to get the idea of conservation, which is not a target for fourth grade. Okay, we're not trying to get there, but we're trying to lay a foundation for it. But the thing that's tricky is you can list these, but you can't learn them sequentially, because you can't really understand forms unless you understand that the way you identify a form is by its ability to transform into something you've already recognized. And you can't understand transfers and transformations unless you understand forms. And you can't understand dissipation unless you understand transfer and transfer. It all falls together. So it's very tricky then to teach. You can't just do, oh, today's our lesson on forms and tomorrow's our lesson on transfer. It doesn't work like that. So to tie all this together, and the goal of this, the way scientists use energy, is to be able to track what's going on in a system or in a phenomenon. That's really the goal. It's not just to have a bunch of facts. It's to be able to use them to analyze some phenomenon. So the thing that pulls this all together is something we call the energy tracking lens. And we use the word lens because energy is just one way to look at a phenomenon. It answers certain questions. It doesn't answer others. So for example, you can use the energy lens, you can use an energy perspective to convince yourself that plants get their energy and are able to grow because they get sunlight, that sunlight is essential to them. That doesn't tell you how photosynthesis works, right? It's not a mechanistic explanation. To do that, you need a different kind of lens, one that actually looks at what's going on. So it's one way of looking at a phenomenon. It's not the only way. It answers certain questions. It doesn't answer others. Okay, so what we ask them, first of all, this is a list that they get. You'll see it again. We tell them, first of all, you start with your observations. What did you observe going on in a phenomenon? And then you try to do what we call telling the energy story. So you have to identify what are the objects, what are the relevant actors in this story, what are the forms that you see that are relevant, where do you see gains and losses happening, where are there transfers happening, where are there transformations happening, and then critically, where does it come from and where does it go? And part of what we're inculcating in them is that this is always a good question. Any phenomenon you've got, it's reasonable to ask this question, where does it come from and where does it go? But all of that has to tie back to what you saw. And so part of the key to this curriculum is that everything they do, no matter what phenomenon it is, they're always using this framework to think about it. So we call this telling the energy story. And that's the goal of energy reasoning, is to be able to tell a story. That's what really we do with energy in science, is we use it to tell a story about the phenomenon, part of the phenomenon. So how do we do this? Well, you need to begin with something to investigate. So we start with activities. So every class, I should say this unit is, depending on how much time they have, is somewhere between 13 and 15 class sessions. Each session's about an hour. And so each session will have an activity, which is something that they investigate. Okay? So these are some pictures of some of the activities. So we start with about 5 classes that are about mechanical energy, where they're doing things like spinning propellers and colliding balls and using springboards. You'll play with some of this later. And then there's a set of activities that are about heat and thermal energy, where they look at transfers going on there. And then they end up with a session that's about electrical and light energy, where they play with generators and capacitors and solar cells and motors and stuff like that. The idea is you're starting with very simple phenomena. The very first thing is just rolling a ball. That's the beginning. You just roll the ball. And you talk about, does it have energy? When does it have more? When does it have less? Then you have 2 balls and you collide them. And you get progressively more complicated until by the end, they're looking at a solar cell. Now you've got the sun, you've got the cell, you've got the wires, you've got the motor, you've got the propeller, you've got the air around it, the environment. It's a very complicated story. But it's the same framework for telling the story. So I didn't say that one of the reasons for doing this, so one reason is energy is an important idea in science, and we would like people to know about it. Some people say just wait, don't tell them about it in elementary school. My view is they're already using the word, they're already hearing the concept. You can't prevent them from knowing something about it. Better they know something correct and useful and accurate instead of just a bunch of vague stuff. But also it's part of the standards. There are Massachusetts standards, there are national standards, and they call for kids at this age to know something about energy. So let's figure out how to do it. So the lessons focus on these core ideas, but they're using practices. They're doing investigation, they're asking questions, they're constructing explanations, and above all, they're developing and using a model of energy. Again, energy is a model. Energy is a conceptual tool that you use. And so in each investigation, they're going to ask a question about this phenomenon. They're going to explore it. They're going to observe it. They're going to collect some data, but by that, it's usually not numbers. It's just observations. Okay? And then they're going to get together in small groups and large groups, and they're going to make some meaning out of this. And in the end, after about every unit or every few classes, they construct collectively a classroom model of rules for how energy behaves. So you wind up with charts like this that are not just written by the teacher, they come from the students' expressions. And they get revised as you go along. They get added to, but they get corrected, things get crossed out. If it's moving, it has energy. That's a starting point, okay? But then you build it up, you build it up, you build it up, okay? And you start to see how the rules, the same rules that you invented that applied for motion, wind up making sense when you're talking about heat and thermal energy too. So they have ownership of this because they've constructed it and they've seen that it makes sense and that using this model, they can construct explanations of all these different phenomena. So it's not just something that's handed to them. This is something they create. We guide them through these activities and through the energy tracking lens in creating it, but we don't give it to them. We give them a framework for building it, but they build it. So they really have ownership of it. Yeah?
How do you see some of the vocabulary, which I think is challenging at this age, like elastic or...
So you let them discuss, that's a great
conservation.
question. Right, so conservation, we don't go there.
Right, but I see there, so the amount of energy does not change. So
Well, so
that's a concept.
they developed that idea. Right. Well, so the question of where does it come from and where does it go, and you'll see when we talk about the representations that we kind of sneak it into the representational schemes. They discovered that, for example, a twisted elastic band must have energy because when you let it go, it makes something move, and they already decided that moving represents energy. We have an activity where they launch a pom-pom from a little springboard, so they conclude that a bent piece of wood has energy. And then you say, okay, so this is energy, and they realize that somehow the amount of energy is related to how much you've bent the springboard or how much you've twisted it. And then you say, okay, so let's have a word for that kind of energy. You say, well, we call those things elastic objects because when you distort them, they come back to their original shape. That's sort of what we mean by elastic. So then let's call that elastic energy. We don't introduce kinetic because it doesn't add anything to the word motion, and motion makes more sense. So we just call it motionary energy. We don't introduce the word potential energy because it just causes problems. People think that it's something that's not moving has potential energy because if you kicked it, it would move and then it would have energy, right? That's not a useful idea. So we avoid terms that you don't need, okay? And sometimes they just say, well, there must be a form of energy here. It's unknown. We'll just call it unknown energy. Yeah.
Talk about gravitational.
So that's a really good question. We deliberately avoid it. So we deliberately avoid gravitational energy.
So they don't have ramps?
They don't have ramps. We try to keep the collisions on a plane. We do elastic. And we made a conscious decision to do that because at this age, for this level, it's better if they can associate, we believe, this is our hypothesis, that it's better if the energy can be associated with an object, right? And the problem with gravitational energy fundamentally is that it's associated with a system. So we've tried to avoid it, yeah.
So what do you do if they observe something falling?
So, I mean, they do, in fact, but it doesn't come up. The teachers bring it up, and we've gotten the teachers, once they learn the energy tracking lens and they learn these representations, they invent gravitational energy with a little help. Because they realize that if you drop something, it started off with no motion energy, and it wound up with motion energy, and then they have to ask the question, where did that energy come from? So they have to invent that there must have been some sort of energy associated with its height. We don't actually go there in the classroom, and it hasn't really come up, I think it's fair to say. Yeah?
Coal.
What about what?
Coal.
Coal or cold?
Coal.
The thing you burn.
Yeah.
So we have not gone to chemical energy. Okay? We have not gone to the energy that is released in chemical reactions. So not just coal. We haven't gone to food. Gasoline, that's something we're struggling with. I think they need to get there eventually. They don't know any chemistry, so we haven't gone there. But it's an excellent question. It's somewhere you need to go. You certainly need to get there eventually. Yeah, but that whole area of chemical energy is something that we have not gotten into.
They know a little bit. You know the train?
It's not like they don't have any prior knowledge about it. I mean, when they see that video of the train, I think you may have come in late, but we showed it. They will say it has energy, not because it's moving. They don't say, I know it has energy because it's moving. They say, I know it has energy because it must be burning fuel or have electricity to make it go. So they certainly have some ideas about it. It's not that they don't. But in our time that we had and the resources that we had available to us, we just decided we couldn't get there. One of the big things we had to decide in the very beginning of this project was all the things we're not going to do. And there's a huge realm of important stuff about energy that we had to make conscious decisions not to do, just because there are limits. And we may or may not have made the best decisions. I'm not certainly asserting that what we've done is optimal. But we had to make choices because there's only so much time.
Roger, I think that one of the ideas that kids come in with, the fourth graders will make statements like, I think that things that are alive or have fuel have energy. So that's what they bring with them, actually. And then you have to disabuse them of the fact that those are the only two of that fact. So I think they're probably thinking about fuel all the time.
Yeah, I mean, the little video clips that we showed you are actually part of an initiation activity that has about 20? 12 different little video clips of all sorts of different things. And we ask them to mark, we give them a little sheet with pictures, and we ask them to mark which ones they think have energy. And if you did that in this room, you would mark all of them, right? And even our teachers who don't know a lot about energy, but they're adults, they'll mark all of them. But the kids don't. The kids mark a very limited number of them, and it's mostly things that are living and moving. And they get in arguments about like an apple or the plant that's growing. And a lot of things that you would think obviously have energy, they don't think obviously have energy. So they come in with a lot of ideas that limit them and that we need to get beyond. But we acknowledge, and they're not bad ideas. They're just not everything. They're not everything you want. They're not in the framework. Okay, so one of the challenges then is, as I said at the beginning, this is fundamentally a quantitative idea. So we need to give them some tools that enable them to tell the energy story in any situation you've got in a consistent way that makes sense and allows them to do this tracking. And that requires some representational schemes. So I'm going to turn this over to Sally, and she's going to tell you a little more about that and let you have a chance to experience it.
This is my first challenge here. Avert your gaze. All right, so a very important part of this program are the representations that we introduce to students, and it's using the representations and learning about them, frankly, is one of the things students like most. Oops, backwards. And the first representation we introduced, we called energy bars. And we introduced them in the context of two colliding balls on a track. And the question that they're investigating is, can a ball cause another ball to move and not lose any energy? And this is a way they collect data. This is their first data sheet. So we try to emphasize that the energy bars are based on observations they've made of the phenomenon. And they've just the one class before, the introductory class, this is only their second class. Their first class, they have a track and one ball, and the question is, can a ball have different amounts of motion energy? That energy isn't an all or nothing thing. And so they've learned if the ball isn't moving, it has no motion energy. And if it's moving very quickly, it has more, etc. So they observe the blue ball, and the blue ball is sitting on the track, not moving. And so the question is, what do we do with the energy bars? And they have 6 of them. They know it's arbitrary. And they say, well, we're not going to color in any energy bars because it's not moving. After the collision, the blue ball begins to move. And then it's up to them to decide how many bars to color in. It's their judgment. This is where we really hand a lot of this over to students. There's no right answer here. It's an answer that is justified by an observation. So they can tell you why they chose three bars. For example, they might say, well, it was moving faster, but it could move faster than that, so it's not 6. So I think it's about 3. And then the yellow ball started with what they thought was 4 bars of energy, and it was moving just a teeny weeny bit at the end, so it got a little piece of an energy bar at the end. And then you'll notice at the other end of the bars, it says, ask them about energy gains and losses. Was there a gain? Was there a loss? Was there no change? And here we see an energy gain in one place is paired with an energy loss in another. So they then collect, they do this 3 or 4 times, and then they use the results of their data to answer that question or to justify their claim that no, it can't cause another ball to move without losing any energy. See, it always lost energy. The next representation, and we brought some materials for you to play with. So I'll introduce this, and then we'll give you something we'll give you some energy cubes and a phenomenon to work with. These are energy cubes, and on your table, I put copies of the energy cube rules. And these are introduced in the context of the springboard and the pom-pom. And this springboard is made, we have the little latch here, for a couple of reasons. One is to get the hand out of the story, because the hand or the person, if it gets in the story, it gets complicated because it doesn't look like I lose any energy when I push it down. I've still got plenty. So we have a latch here, whoops, and we put a pom-pom on. The other reason we have it, this material, is for safety's sake, which is that it limits how far things can fly. Now, so far in the classroom, we have not seen people launch things other than the pom-pom, but it's possible. So we pull the latch back, and the pom-pom, this is very popular. So in terms of, this is where we introduce energy cubes. They use energy bars to describe this energy story first in their notebooks, and then we introduce the cubes. The energy cubes, I'll give you a set in a minute, are just little clear lucite cubes, and we put stickers on to represent different forms of energy, and to reinforce the idea that whether it's motion energy or elastic energy, it's all the same stuff. It's the same cube, and these are arbitrary units of energy. So here's a little energy cube. Each cube represents a unit of energy. This is on your table so you can see it. And then when you use energy cubes, we give them whiteboards. I brought you paper today. And they use circles to decide what the important components of the system are that are part of the energy story. So what are the objects, or what are the interacting components that are critical to the energy story? So they're regions. And we give them whiteboards, markers, and erasers because we found that it's important to allow them to try things out, erase it, redo it, relabel, redraw, add, etc. But anyway, we brought you some paper instead of a whiteboard today. So in the case of the colliding balls, they decide it's possible with the colliding balls. Somebody might say, okay, the system is the hand that launches the ball, the two balls, and the track. And then they have a discussion. Well, is the hand really important when we're trying to answer a question about collisions of two balls? Do we need the hand? Does the track really come into this, play a role in this energy story, or is it just something to keep the balls from flying off the table? And so they end up, most of them, with a little help from their teacher friends, to having the two regions, the two circles being ball A and ball B, or red ball, blue ball. But this discussion of what are the components, the important parts of the components in this interaction is important. And there, once again, you may see whiteboards that are non-identical. And that, of course, raises some interesting conversations. So each cube is the form of energy with the face with the form up, M for motion. Now, in this case, we have a transformation where we start with the paint paddle having elastic energy, and then after release, it's transformed into motion energy. So if I have a paint paddle circle, and I have an elastic energy cube in the circle, to show the transformation, I just flip it to motion. And again, it's interesting to watch where the kids, where in the energy story, what areas, where does the cube flip? You know, sometimes you'll see cubes flipping in the air, sometimes you see it sliding, etc. The number of cubes corresponds to the quantity, and Roger talked about quantification here, and so we get in a little bit of quantity, sort of semi-quantitative, when we use cubes or bars. And the number of cubes in a region corresponds to the quantity of energy in that cube. To show transfer, cubes slide or move from one region to the other. So the cube will be picked up and moved from the paint paddle to the pom-pom. Now, students start, and you will in a minute. Here's what happens in the classroom. They start with a blank piece of paper, a whiteboard, a set of markers, an eraser, 6 cubes. And it's very important that we actually give them the object that they're trying to analyze or tell the story of. So they have the object to play with. And we see them going back to the object over and over and over again to look more carefully as they tell the energy story. Whoops. Students decide which objects to represent. And again, the title of this talk is Real Science. And so students really drive the bus. That's Roger's wonderful term. I think it's great. They make lots of decisions. They decide which objects to represent, which forms of energy are present, and how to move and flip the cubes to tell the energy story. And once again, whiteboard stories that are then shared among the classes are almost never identical. And that means that the class collectively is developing an understanding collectively. They're learning from each other. They're being questioned and saying, what do I think? So here's the paint paddle and the pom-pom. You just saw it. It starts all elastic and nothing in the pom-pom. And then, of course, we say, well, how did you decide? Well, it wasn't moving. It wasn't deformed. At this point in the unit, they only know 2 forms of energy. Now, as the paint paddle is released, the pom-pom flies into the air, but they observe that the paint paddle is still moving. And if it's moving up and down, at some point, it's a little bit bent. So it's got to have a little bit of elastic energy left over. So again, they're linking their abstract representation of the phenomenon and being able to tell you what they're thinking. And now the pom-pom is at its height probably, and the paint paddle has a little bit of motion still, and it's a little bit deformed. We're going to stop right here, and we're going to give you a chance to try this out. So just work with somebody, take 6 cubes, and we're going to, here's the phenomenon, and here's markers. Markers? Broken. Yeah, just one marker, that's all they need. All right, and what you're going to be, Roger, do you want to pass those out? All right, here's the phenomenon. Maybe we could turn the lights on. Oh, good. All right, here's your system today, and this follows the paint paddle and the ping pong, and it's just a rubber band propelled. We just took apart a balsa wood airplane. All right. So here's your challenge. We want you to, kids in the classroom begin to use the verb to cube. We want you to use energy cubes to tell the story of the elastic band propelled propeller. So you've got the object in front of you. You've got the energy, I handed out energy cube rules. You've got a set of rules there for you to follow. And so the first thing you're going to decide after observing this is what are the important or critical components of the system? What are the circles you need on your paper? Can you see how they have circles up there in their whiteboards? And that one is the solar panel. They have a propeller, solar panel, wires, etc. How many circles are you going to have? And what are you going to name them? Where do you start the cubes? And by the way, we suggest that they start in the classroom, that they start this energy story. When they cube the story in their whiteboards, they start with the propeller fully wound. Obviously, they could go back and say, I'm going to start with a hand and so on and so forth. We say, and wind it no more than 20 times. We'll give you, about 7 minutes to do this or so. Talk to your friends. Any questions? Here.
We'll just use a little.
Here, use this. Here, use this one.
You sure?
I think
I'll break this one too.
No, I'll get you. Somebody else hold it.
One.
Did you wind it more than
It came broken when I put the plastic thing back on the balsa. Broken yet.
Are you working together here?
Yeah.
I'm taking notes.
No, you have to do the cube story.
He's supervising them.
No, come on.
No, I'm looking at the reference first.
All right.
So what we got? We got an airplane with that.
It's here, and we could do intermediaries, but everything's going to migrate over there. Except for the fact that the elastic is
Winding up the rubber band. And then when you let go, so this is the start of the system because it's wound up. So you let go, and then the propeller will move, and then we feel a breeze.
They said start.
Okay, so what are your how many circles will you have?
Okay, so I think we need a rubber band circle, right?
Okay.
We need a propeller circle and an air circle.
Okay. And you can put them anywhere on your thing, but make them big because you're going to be able to put cubes in them.
Okay.
And so are you? And if you started here, where will your cubes be? What will your cubes be? Well, why don't you do your circles?
Okay.
Now, what are your circles?
Diagram.
Well, now do your
But you
circles.
will do a circle.
You may have to take away the marker.
Are there only
I was
are
gonna
there
make
only-
square,
Are there
just
only
to be
two
different.
circles? How many does that have? So
All
how
right.
do you get, how much scaffolding, I mean, obviously, forget the problem child, but how much scaffolding do you need? Because before you're talking about, oh, and then they have conversations about this, but how much scaffolding or how many times do you have to do it to get the small groups to have conversations versus one person say, all right, I'm doing it.
That's a good question. We may model it before, and as a class come up with the circles or not. You have to look at your class. Now they will have done this once with the propeller and the pom poms, so they haven't done it all that many times.
Right. Yeah, I'm just curious because with some of our projects, it's just hard to get them to choose. We always say, oh, they're going to have these great discussions about whatever.
Well, these kids talk, and it's partly because we've put so many things to talk about in their hands. All right,
So
now
we have the rubber band. What's this?
Wood. Which is not that elastic, by the way.
I feel like that might be a separate.
No, and what's this air?
okay.
Which one represent the different stages of the
That's a good question. Sometimes they'll have 3 sets of circles. There was a slide back there. Let's see if I can show you.
I think that's where they don't want to, or like a pump.
Oh, actually,
I think it's like that worksheets.
oh, you can't really see it here, but in some cases they'll say time 1, time 2, time 3. So they'll tell the story, and they'll say, okay, let's start with the propeller fully wound and nothing's moving. Now let's start with the propeller moving, the rubber band unwinding, but everything's still in motion. And that's the next low. Let's do that. So they do 3 sets of circles.
I see. And what do they do with the cubes? Do they also address the end phase where nothing's in motion again?
Ah, very good question, because when they get the cubes here to the propeller, eventually the propeller stops moving.
Right.
And so now the question is they've got to be able to answer the energy, all of these energy lens questions in their discussion. Where did the energy come from? Well, it came from the rubber band.
Yeah.
Where did the energy go? Good question. And now they begin to talk about that. And they may draw, we've seen various, they may draw another circle. They may say air. They may say somewhere. They may say question mark. And when they move the cubes, they may say, well, we think it moves to the air, and it's motion energy because I can feel the air moving. Great evidence. But again, eventually that will stop too.
Right.
Or if they say somewhere and they don't know what the form is, we've seen many groups just turn a blank side up and say, we don't know.
Yeah.
But the energy has to be somewhere.
Right. And this is still representing that.
Yeah,
energy,
yeah.
right?
And so all 6 cubes, all of the 6 cubes have to be used all the time. You have to account for all of them all the time.
What's the most labels you ever put on one cube?
Well, in our curriculum, we end up with thermal, electrical, light. That's it. So we have enough faces. But they do ask, and one of the things they're amazed by is the fact that if you take the propeller at that stage when it's unwinding, what does your cube story look like when it's still unwinding?
When it's still unwinding, we
Yeah.
had something along the lines of wrong.
Yeah, so now the question is, can an object have more than one kind of energy at the same time?
Yeah.
And then they'll say, well, how many kinds can it have?
Like,
Maybe they understand it if you say, well, if you stir something really hard, then it gets warmer.
Yeah, maybe.
So this became air.
Yeah.
Yeah. And what did you do with these two cubes? You have to.
We think they're losses.
They're losses.
Yeah.
They're heat losses.
All right. So eventually we'll have.
Yeah, something.
We have a TH, which is for thermal, which will be added the next class.
Sure.
Or if the kids don't know what they are,
course not.
they
You
leave
can't see them.
they leave the blank side up, and they say they may have a circle that says somewhere, and they don't know what the form is. But they are able to justify this. Now, some kids will say, I think let's assume you start with motion. You've got motion here. Let's do something like this. Is that reasonable? And they'll say, well, some of the motion from the propeller will go there, but some of the motion to the air comes from the rubber band, because they believe that as this rubber band unwinds, it's pushing the air, it's transferring to the air. So they may take one of these cubes and move it directly to here.
It's not totally wrong. It's just
It's
infinitesimal, right?
But it's using those indicators in their reasoning to say, well, it must be pushing the air. So their energy cube story may look different than somebody else's. On the other hand, when they report it, the other kids will say, "Oh, cool, yeah, that's interesting." All right, are we all finished? What comments? Questions? Well, first of all, this is the most wonderful practical assessment a teacher could ever have. Because I could go around to your cubes, I did, to some of you, and I can see.
Right.
And you can tell me what your reason
Right.
is.
So, but that's my question. So yes, you absolutely can do that. But if you've got 20 groups going, and how do you get to all of them? And or do you have us write the story, sort of what we ended up doing? Because we have something here that was very different than what was going on during.
Correct, and that is a bit of a problem. And this pair over here said, well, how do you show the process,
Right.
not just the beginning and the end? And we teach them how to do time 1, time 2, time 3, and 4 example. And so they can say, all right, we're going to start time 1 when nothing's moving. Fully run, and they'll have 3 circles.
Right.
Rubber, elastic band, and propeller air. Then time 2 is typically as the rubber band is unwinding, the propeller is moving, but it's not fully unwound.
Right.
So it's still got some elastic energy, it's in motion, and the propeller's in motion. Time 3, everything's still.
Well, maybe that's time 5.
Yeah.
Well,
There's a long time.
Yeah, exactly. I mean, it might be time 5, but they can do as many times as they want.
All right, so that's what I was asking about.
Yeah.
That was the important part to me of the story, not just the beginning and the end, but all the things that happened in
But the
between.
real story is the movement of the cubes.
Right.
And in a classroom as a teacher, we have to work in groups of 4. And it's actually pretty easy in 15 minutes, say, to move around to all 4 groups. I've done it quite a few times in the classroom. So it's pretty easy. Now, what happens during the small group work, what you just did, is that's the time for kids to really try out their ideas with no penalty. Partially formed ideas, questions, and we've got on tape, we've got on video, some just terrific video of these kids. One of the ones I love the most are 4 students, and it's hard to believe they've only had 2 classes before, or 3 classes before they start this, but talking about when the pom-pom lands, where did the energy go? And they've had 3 classes. They're actually, these were 5th graders, but they're saying, whoa, where did it go? And so they're able to throw out all these ideas. And one of them is trying to talk about what happens in the air. Did it leave some of the energy in the air? When it landed, they say, well, maybe it gave the energy to the rug, but it bounced a little, so not all of it. I mean, that's the kind of discussion that when you hear it, you think, oh, my man, this is amazing. And when I heard that discussion, and later we saw it on videotape, I mean, we were kind of blown away. And then that same group of kids, and then there's one quiet boy. There were 3 very chatty girls and one very quiet boy, and you hear him in the background saying, I think it goes to the air and spreads out everywhere. Nobody pays any attention to him. But eventually they flip, and they have their springboard and pom-pom. They flip it up again and watch it land in this, and the girl picks up her whiteboard a little bit and lets it land on the whiteboard, and what she's trying to see is if it makes the whiteboard move. They know that they say it doesn't have enough energy to make the floor move. We can't observe that, but maybe it can make the whiteboard move. I mean, they didn't say that, but that's what they were doing. And then they're saying, nope, the pom-pom just doesn't have enough energy. But they are thinking it's got to go somewhere, and they're thinking, well, maybe here's a test so we could figure out if it does go to the whiteboard. And so they actually design and do a little experiment all in that less than 1 minute event. We did this in a number of districts around Boston. We don't usually identify them except to say local districts, but we worked primarily with Malden and Newton. We did some work in Belmont way back in the very beginning, and in Burlington.
And what's your end number in a classroom? Range? And typical?
Usually around 22 or plus or minus. Well, not many more.
30.
Well, yeah, 30 involved.
Yeah,
With
that's what
typical
we're
one
curious about
facilitator,
is
One teacher.
is the 30, like you get different outcomes in a class of 30 versus a class of 20?
It's hard to attribute different outcomes to one factor, because if you take a class of 30 in Malden and compare it to a class of 22 in Newton, there are other factors that may play as big a role. So I would never want to put my money on class size as the deciding factor. Now, any other comment on the cubes? Did you have fun?
I want more cubes.
Everybody who has cubes loves cubes.
What do the kids do at the end to represent the fact that the energy has to go somewhere? So we finish and all of our cubes are in the air circle.
Yeah.
And then what?
Well, that's a really good question. They have to decide ultimately where the end is. Now, after they have the thermal energy unit, which would follow this, they say to the air and they flip it to thermal energy. And they almost learn it a little bit as a mantra. I'm not convinced that they totally get dissemination or dispersion, but they'll flip it. And then I've watched kids who have this rule, well, it must be thermal energy. It must go to the air and turn into thermal energy. That's the end. Well, it's not such a bad mistake, I guess, to have as a partially understood mantra. But that's one thing they do. They do end up with a circle that says somewhere, air, environment is a typical circle. A circle may say unknown, and you may end up with a cube with a blank face up. They say, we don't know, it's not motion, it's not elastic, it's not thermal, but we don't know any other forms yet. But it's some form.
Do they use the yet language to kind of draw attention to the fact that they don't know that everything that's out there, but there are other things that are out there?
Well, they don't use it because they're talking so fast. Okay, we have another great video of the solar panel where they're dealing with solar energy and they don't really know much about it yet. They're wondering whether the energy right from the solar panel is light or thermal. And they actually do a little experiment. They're very quick to figure this out. They say, well, if we turn the solar panel over, the propeller stops, but the temperature hasn't changed around the panel. So it must be light. They've really learned a way to reason about energy flow. That's the bottom line. Yeah.
But isn't it rather theological for them to argue it must go somewhere? Because you told them it doesn't.
Well, one said energy heaven, so yeah, I guess.
That's a belief that you tell them, and then they don't have evidence for it.
I would argue that that's what we as scientists do, though, right? I mean, has anyone in this room actually seen a quantitative demonstration of conservation of energy in a dissipative context? Have you ever actually had a situation where the energy was dissipated and it was all measured and you could account for all of it?
Dissipated to where?
Well, like into the air, into like a normal thing, like rolling sliding a box across the floor and actually measuring where all the energy went. I have never done it. But it's in a very limited case, right? But most of us in real life situations have never done that. But we have developed a belief that this is plausible because we've seen some limiting cases and we've seen that this whole picture can hang together. So it's a model that is self-consistent. Whether that's theological or not, I don't know. But
they do develop sort of a mantra that they get because they see it every single time. They say, whenever there's a gain, there's a loss. And we have actually, of course, sort of engineered it so that they usually can see at least one gain and loss in every single circumstance. But they've become to really believe that, and so that we planted that seed for that they'll think that later on. I have to say that when we first started this project, we interviewed teachers and students, and we found one refrain was, we would say, okay, and then where does the energy go? And they'd say, it's just gone. And they had a commitment to lack of conservation. And so we were really interested in trying to sow the seeds of, just sort of believing it must have gone somewhere. So yeah, maybe it was a little bit drink the Kool-Aid, guys, and theological maybe. We're apparently out of time now, so I wanted to really quickly, let's see, what's the most, I'm going to show you some results, and I just want to show you that we used this as a pre-post, and it's a little toy called Sparkles, and the kids play with it, it sparks, and makes noise, and it has a spring in the middle, and we asked them to tell an energy story about it when they first come in, and they all go, oh great, I'm going to tell an energy story. And I don't have the slide up right now because I'm doing really quickly. But basically it's like, yeah, I can tell an energy story. I turn the crank and it moves the gears inside and then the wheels turn and they're little sparks. And that's their energy story. And they'll write a whole page about it. And there's nothing about energy in the story at all. It's mechanistic. By the time they leave, they'll either use words or often diagrams of something like this where they're showing things like this. And you can see here that they have 6 motion energies in the crank, and then they have it go to the gears, and they have it go to the scraper, and then off to the environment, the cubes, and they're saying unknown energy in the environment. So that's a kind of way that they might describe that. And I think in this case they have a hand also that has unknown energy. So they're raising more questions. It's a pretty amazing transformation. And so I'm just going to quickly show you a graph of some results. This is for teachers, but I'm get right to the students, right? So we graded it, we scored it. We looked for forms of energy in their story. We looked for transfer and transformation. So it's sort of how many forms they mention. Transfer and transformation, and so we're looking to see if they show that one cube turns to another, another face, it goes from M to E or to blank or something else, and whether they show that the cubes are actually sliding. Is there a sense that the same energy is moving, or is it just sort of snapshots that sort of somehow magically this energy was there and then that appeared there? And then we're looking at dissipation, which is really just an evidence that it's not gone, it's somewhere at the end. And then...
and just to say, those look a little low. Nothing in the prompt asks them anything to suggest that they should say anything about that. There's no question, where does it go at the end, or... So that's, they voluntarily, without any prompting, included something.
And it's really not part of the curriculum.
And it's really not part of the curriculum either. So we just included that because we were curious about it. But it's a little unfair to expect it even.
And then, as Roger said in the beginning, we're really interested in the overall coherence of this story, their ability to use these ideas together. You know, the research shows that the traditional way of teaching about energy, where kids learn first forms in one grade and then transfer in another grade, and then they get to eventually to conservation and maybe dissipation, isn't working at all. So the theory is that if you can somehow give them this framework to be able to start talking about everything together and make a coherent story, that might be a better way to start out. So that was our goal. So we wanted to be able to see if they could use all the ideas together to tell a story about sparkles. So what we found here is we have, you can see that the pre-tests for control and treatment, that basically they don't have much to say about energy at the beginning, that we have those stories like the one I told you, where that it's just about a mechanism. They're happy to write about it, it's a fun assessment for them, but they really don't have much to say about energy. And after the control kids had a business as usual energy class, and they got pretty good actually at talking about forms of energy. They identified some forms of energy by the end, but kids we worked with identified more. And then for transfer and transformation, they learned some about transfer, and they even learned some about flow. But by the time you start getting to flow, our kids, we really focused on flow and this overall coherence of the story. And you can see that that there's just huge gains from knowing, you know, any energy class is going to teach them a lot. But by giving them this sort of coherent system and framework for looking at energy, they really make tremendous gains, and they're able to tell a pretty coherent story, and even to include dissipation when we don't ask about it. So we're very pleased and surprised, actually. Yes.
Do you know what was in the business as usual curriculum, and like sort of was it matched in like the 13 to 15 sessions?
No.
Not entirely, but on the other hand, that's pretty typical of an elementary curriculum unit. That they get science like 1 or 2 days a week.
But it's a fair point. Some of this is just time on task. Some of the difference between control and treatment is just this was an extended, focused thing about energy, and the other things were often things like circuit units that involve something about energy. So, I mean, I think that's a fair comment that part of this is just
that there wasn't anything about energy.
They got a lot more about energy.
That there wasn't anything.
Can we just show the last video?
Oh, what other pizza do you want to do?
Can we? Yeah, we should get over all the weekend. Play that.
But we can still do questions.
So let's thank the speakers for. We have to ask more questions as we all look and whatnot. So, thank you. Might be easier to. I don't know which would be easier to actually be able to focus on the video, because people will keep like looking at that.
Absolutely happy doing it.